Let's talk about the shape of the orbit. One interesting question we would like to ask is whether there will be an orbit closure. In other words, if we trace the planet's trajectory, the question is whether the orbit will close on itself. The answer is generally no, except when the period of radial motion divided by period of angular motion is a rational number. An interesting result is that the orbit is not closed except when the potential is that of the gravity, or the force being proportional to the inverse squared radius. This is the case of Kepler problem. And in the case of Kepler problem, we have orbit that's one-to-one closed. In other words, the period of motion in radius and the period of motion in angle are the same. Another interesting question to ask is when orbit is stable. This is an important question that has large implications on planetary dynamics. To answer these questions, let's first find the equation for the orbit shape. We start out with the equation of radial motion. We're using general form of the radial force, which is simply du dr with a minus sign, and we want to make the following substitution and solve small u as a function of theta, not as a function of time, to figure out the shape. So to avoid any confusion, we are not going to use u, the potential energy. So another equation, of course, is angular momentum conservation. So our job is to work with the radial equation of motion and to extract an equation that will relate u and theta, differential equation. So to do so, let's first write time derivative operator. We can write it in terms of d theta dt and then d theta. Or it's going to be theta dot d theta. Or we can further simplify it by replacing theta dot with the angular momentum, L divided by mu r squared, d theta. And then we replace u, the inverse of r, and we get Lu squared over mu d theta. Thus, we can write r dot as d dt of r, or using the expression for d dt that we just found, Lu squared divided by mu d theta of 1 over u, which is simplified to minus L divided by mu and then u prime. Here u prime is defined as du d theta. Next, we find r double dot, which is obviously d dt of just r dot, or Lu squared over mu d theta, and we substitute the value for r dot that we just found, minus L over mu u prime, which is equal to minus L squared u squared divided by mu squared times u double prime. We substitute all of this into the radial equation of motion, and we get minus L squared U squared divided by mu U double prime equals F, the form of the force, general form, plus L squared U to the third power divided by mu. Or after some rearranging, we get U double prime theta equals minus U of theta minus mu divided by L squared U of theta squared times F, which is itself a function of U of theta. We note that in this equation, these two terms here look like simple harmonic oscillator, whereas the last term on the right-hand side is a nonlinear term with theta. We see that the motion for arbitrary dependence of the force with r is very complex, except when the force is given by the inverse radius squared, or minus ku squared, in which case we're gonna get from the equation for the orbit u double prime of theta equal minus u of theta plus, and we're gonna get k mu divided by L squared, which is just a constant. So we see only when the force is proportional to the inverse radius squared that the orbit equation becomes very simple and will close on itself.